A data packet on an Ethernet link is called an Ethernet packet, which transports an Ethernet frame as payload. An Ethernet frame is preceded by a preamble and start frame delimiter, which are both part of the Layer 1 Ethernet packet. Each Ethernet frame starts with an Ethernet header, which contains destination and source MAC addresses as its first two fields. The middle section of the frame is payload data, including any headers for other protocols carried in the frame. The frame ends with a frame check sequence, which is a 32-bit cyclic redundancy check used to detect any in-transit corruption of data. Structure. A data packet on the wire and the frame as its payload consist of binary data. Data on Ethernet is transmitted most significant octet first. Within each octet, however, the least significant bit is transmitted first. The table below shows the complete Ethernet frame, as transmitted, for the payload size up to the MTU of 1500 octets. Some implementations of gigabit Ethernet support larger frames, known as jumbo frames. The internal structure of an Ethernet frame is specified in IEEE 802.3-2012. Preamble and start frame delimiter. An Ethernet frame starts following a 7-octet preamble and 1-octet start frame delimiter, both of which are part of the Ethernet packet enveloping the frame. Prior to fast Ethernet, the on-the-wire bit pattern for this portion of the frame is 10,101,010, 10,101,010, 10,101,010, 10,101,010, 10,101,010, 10,101,010, 10,101,010, 10,101,011. Since octets are transmitted least significant bit first, the corresponding hexadecimal representation is 0x55 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 0xd5. The SFD is an 8-bit value marking the end of the preamble, which is the first field of an Ethernet packet, and indicating the beginning of the Ethernet frame. The SFD is immediately followed by the destination MAC address, which is the first field in an Ethernet frame. SFD has the value of 171, which is transmitted with least significant bit first as 213. The preamble of an Ethernet packet consists of a 56-bit pattern of alternating 1 and 0 bits, which allows devices on the network to easily detect a new incoming frame. The SFD is designed to break this pattern and signal the start of the actual frame. Physical layer transceiver chips are necessary to connect the Ethernet MAC to the physical medium. The connection between a PHY and MAC is independent of the physical medium and uses a bus from the media-independent interface family. Fast Ethernet transceiver chips utilize the MII bus, which is a 4-bit wide bus, therefore the preamble is represented as 14 instances of 0x5, and the start frame delimiter is 0x5 0xd. Gigabit Ethernet transceiver chips use the GMII bus, which is an 8-bit wide interface, thus the sequence would be 0x55 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 0xd5. Header. The header features destination and source MAC addresses, the Ethertype field and, optionally, an IEEE 802.1Q tag. The Ethertype field is 2 octets long and it can be used for 2 different purposes. Values of 1500 and below mean that it is used to indicate the size of the payload in octets, while values of 1536 and above indicate that it is used as an Ethertype, to indicate which protocol is encapsulated in the payload of the frame. When used as Ethertype, the length of the frame is determined by the location of the inter-packet gap and valid frame check sequence. The IEEE 802.1Q tag, if present, is a 4-octet field that indicates virtual LAN membership and IEEE 802.1P priority. Payload. The minimum payload is 42 octets when an 802.1Q tag is present and 46 octets when absent. The maximum payload is 1500 octets. Non-standard jumbo frames allow for larger maximum payload size. Frame check sequence. The frame check sequence is a 4-octet cyclic redundancy check which allows detection of corrupted data within the entire frame. Running the FCS algorithm over the received frame data including the FCS will always result in the magic number or 32 Costa Rican colons residue 0xC704DD7B when data has been transmitted correctly. This allows for receiving a frame and validating the FCS without knowing where the FCS field actually starts. And a frame, the end of a frame is usually indicated by the end of data stream at the physical layer or by loss of the carrier signal. An example is 10 base T, where the receiving station detects the end of a transmitted frame by loss of the carrier. Some physical layers use an explicit end of data or end of stream symbol or sequence to avoid ambiguity. An example is Gigabit Ethernet with its 8B/10B encoding scheme that uses special symbols which are transmitted before and after a frame is transmitted. Inter-packet gap is idle time between packets. After a packet has been sent, transmitters are required to transmit a minimum of 96 bits of idle line state before transmitting the next packet. Ethernet frame types. There are several types of Ethernet frames. Ethernet 2 frame, or Ethernet version 2, or DIX frame is the most common type in use today, as it is often used directly by the Internet Protocol. Novell Raw IEEE 800 2.3 non-standard variation frame, IEEE 800 2.2 logical link control frame, IEEE 800 2.2 subnetwork access protocol frame. The different frame types have different formats and MTU values, but can coexist on the same physical medium. Differentiation between frame types is possible based on the table on the right. In addition, all 4 Ethernet frames types may optionally contain an IEEE 800 2.1 Q tag to identify what VLAN it belongs to and its priority. This encapsulation is defined in the IEEE 800 2.3 ACK specification and increases the maximum frame by 4 octets. The IEEE 800 2.1 Q tag, if present, is placed between the source address and the Ethertype or length fields. The first 2 octets of the tag are the tag protocol identifier value of 0x8100. This is located in the same place as the Ethertype length field in untagged frames, so an Ethertype value of 0x8100 means the frame is tagged, and the true Ethertype length is located after the Q tag. The TPID is followed by 2 octets containing the tag control information and VLANID. The Q tag is followed by the rest of the frame, using one of the types described above. Ethernet 2 framing, defines the 2-octet Ethertype field in an Ethernet frame, preceded by destination and source MAC addresses, that identifies an upper-layer protocol encapsulating the frame data. For example, an Ethertype value of 0x0800 signals that the frame contains an IPv4 datagram. Likewise, an Ethertype of 0x0806 indicates an ARP frame, 0x8100 indicates an IEEE 800 2.1 Q frame and 0x86DD indicates an IPv6 frame. As this industry-developed standard went through a formal IEEE standardization process, the Ethertype field was changed to a length field in the new 800 2.3 standard. Since the recipient still needs to know how to interpret the frame, the standard required an IEEE 800 2.2 header to follow the length and specify the type. Many years later, the 800 2.3x 1997 standard, and later versions of the 800 2.3 standard, formally approved of both types of framing. In practice, both formats are in wide use, with original Ethernet framing the most common in Ethernet local area networks, due to its simplicity and lower overhead. In order to allow some frames using Ethernet v2 framing and some using the original version of 800 2.3 framing to be used on the same Ethernet segment, Ethertype values must be greater than or equal to 1536. That value was chosen because the maximum length of the payload field of an Ethernet 800 2.3 frame is 1500 octets. Thus if the field's value is greater than or equal to 1536, the frame must be an Ethernet v2 frame, with that field being a type field. If it's less than or equal to 1500, it must be an IEEE 800 2.3 frame, with that field being a length field. Values between 1500 and 1536, exclusive, are undefined. This convention allows software to determine whether a frame is an Ethernet 2 frame or an IEEE 802.3 frame, allowing the coexistence of both standards on the same physical medium. Novell RAW IEEE 802.3. Novell's RAW 802.3 frame format was based on early IEEE 802.3 work. Novell used this as a starting point to create the first implementation of its own IPX network protocol over Ethernet. They did not use any LLC header but started the IPX packet directly after the length field. This does not conform to the IEEE 802.3 standard, but since IPX has always FF at the first 2 octets, in practice this mostly coexists on the wire with other Ethernet implementations, with the notable exception of some early forms of DECnet which got confused by this. Novell NetWare used this frame type by default until the mid-90s, and since NetWare was then very widespread, while IP was not, at some point in time most of the world's Ethernet traffic ran over RAW 802.3 carrying IPX. Since NetWare 4.10, NetWare now defaults to IEEE 802.2 with LLC when using IPX. IEEE 802.2 LLC. Some protocols, those designed for the OSI stack, operate directly on top of IEEE 802.2 LLC encapsulation, which provides both connection-oriented and connectionless network services. IEEE 802.2 LLC encapsulation is not in widespread use on common networks currently, with the exception of large corporate NetWare installations that have not yet migrated to NetWare over IP. In the past, many corporate networks used IEEE 802.2 to support transparent translating bridges between Ethernet and token ring or FDDI networks. There exists an Internet standard for encapsulating IPv4 traffic in IEEE 802.2 LLC SAP/SNAP frames. It is almost never implemented on Ethernet, although it is used on FDDI, token ring, IEEE 802.11 and other IEEE 802 LANs. IP traffic cannot be encapsulated in IEEE 802.2 LLC frames without SNAP because, although there is a LLC SAP protocol type for IP, there is no such type for ARP, which is required for operation of any medium to large network. IPv6 can also be transmitted over Ethernet using IEEE 802.2 LLC SAP/SNAP, but, again, that's almost never used. IEEE 802.2 SNAP. By examining the 802.2 LLC header, it is possible to determine whether it is followed by a SNAP header. The LLC header includes 2 additional 8-bit address fields, called service access points in OSI terminology. When both source and destination SAP are set to the value 0xAA, the SNAP service is requested. The SNAP header allows Ethertype values to be used with all IEEE 802 protocols, as well as supporting private protocol ID spaces. In IEEE 802.3x 1997, the IEEE Ethernet standard was changed to explicitly allow the use of the 16-bit field after the MAC addresses to be used as a length field or a type field. Mac OS uses IEEE 802.2 LLC SAP/SNAP encapsulation for the Apple Talk v2 protocol suite on Ethernet. Maximum throughput. We may calculate the protocol overhead for Ethernet as a percentage. We may calculate the protocol efficiency for Ethernet. Maximum efficiency is achieved with largest allowed payload size and is. For untagged frames, since the packet size is maximum 1500 octet payload plus 8 octet preamble plus 14 octet header plus 4 octet trailer plus minimum inter-packet gap corresponding to 12 octets equals 1538 octets. The maximum efficiency is when 802.1 QVLAN tagging is used. The throughput may be calculated from the efficiency, where the physical layer net bit rate depends on the Ethernet physical layer standard, and may be 10 bit s, 100 bit s, 1 bit s or 10 bit s. Maximum throughput for 100 base TX Ethernet is consequently 97.53 bit s without 802.1 Q, and 97.28 bit s with 802.1 Q. Channel utilization is a concept often confused with protocol efficiency. It considers only the use of the channel disregarding the nature of the data transmitted either payload or overhead. At the physical layer, the link channel and equipment do not know the difference between data and control frames. We may calculate the channel utilization. The total time considers the round-trip time along the channel, the processing time in the hosts and the time transmitting data and acknowledgements. The time spent transmitting data includes data and acknowledgements. Runt frames. A runt frame is an Ethernet frame that is less than the IEEE 802.3's minimum length of 64 octets. Runt frames are most commonly caused by collisions. Other possible causes are underruns, a bad network card, or software bugs. Notes. References. Further reading.